This is the last topic for this week and is solutions by power series. We are looking at second order non-constant coefficient ODE, y second, second derivative of y plus px first derivative of y plus qx y equals to 0. And we're interested in the solution at a certain value x0. What we do is use the Taylor expansion of p and q at x0. So we expand p around x0, that is, we write instead of px, we write px0 plus p prime x0 times x minus x0 plus p second prime x0 divided to factorial times x minus x0 squared, and so forth. All of that multiplied by y prime plus the same Taylor expansion for q multiplied by y. At the beginning we have a y second prime. All of this is equal to 0. And we have a theorem that says that if both p and q are analytic at x0, then every solution of the ODE is analytic. Just a reminder of what analytic means. A function is analytic at a point x0 if the Taylor series of that function centered at x0 converges for all values of x in a neighborhood of x0. If this is true, then x0 is called a regular point. By the theorem that we just said, then we can write the solution to our ODE, so y, as a potentially infinite sequence of ak times x minus x0 to the power k. Small typo in the slides. But now we have to find all these coefficients a0, a1, a2, and so forth. So let's try to look at this. Let's try and look at some examples for it. Let's look at the first example being second derivative of y plus y equal to 0 around x naught equals to 0. We know that the solution is a combination of sine and cosine, but we would like to prove this through power series method. So by analyticity, y can be written as an infinite series, an infinite power series. So a series of ak xk. And now we're looking at trying to find ak. So let's try to write y as the sequence. So it's y equal a naught plus a1x plus a2x squared plus a3x third, and so forth. The first derivative, well, the first term is 0, it's a constant. The second term, x disappears, so we only have a1. The third term, we have 2a2 times x, then we have 3a3 times x squared, and so forth. We can write it as the sum for k going from 1 to infinity of k times ak times x to the power k minus 1. Or we can rename the variables inside this sum. These variables are only inside the sum, that's why we can rename them. I will introduce n being k minus 1, so our sum now goes from n equal to 0 to infinity. I replace k by n plus 1 and k minus 1 by n. So now I have a sum from n going to 0 to infinity of n plus 1 times n plus 1, that is the index of a, times the power n, the nth power of x. We do the same thing for the second derivative. We find that the second derivative is the sum from k going to 2 to infinity of k times k minus 1, ak, x at the power k minus 2. And I changed the index of the sum. Now I want the sum to go from 0 to infinity. So I introduce an m that is equal to k minus 2. And k becomes m plus 2. K minus 1 becomes m plus 1. And k minus 2 becomes m. So now I have a sum from m going to 0 to infinity, m plus 2 times m plus 1 times a index n plus 2 times mth power of x. N, k, and m are all dummies. They only live within the sum that we're looking at. So we can change their names anytime we want. We can also, as you have seen, change their values. And as long as they're all coherent all the time, this is something we can do. So let's go back to our ODEs. We have m second plus y second derivative plus y equal to 0. We replace the second derivative inside. We replace y with its power series. And we change the dummies to have the same name. So we think we can merge the sums together. So we have an infinite sum from n equal to 0 to infinity of the product of n plus 2 and n plus 1 times a at the index n plus 2 times x to the power n. All this chunk plus a to the n, x to the n equal to 0. X to the n appears on both terms, so we can take this out of this big parenthesis. It's still inside the sum. So we have a block of things depending on n and a's, multiplies by xn, summed for all n equals 0 to infinity. It holds that a power series is equal to 0 only if every single term within the power series is equal to 0. Why is that? Well, because x can take any value that we want. So if you're able to multiply different terms with different values and constantly have equal to 0, then it means that every single term is equal to 0. So we now know that there is a relationship between an plus 1 and an such that n plus 2 times n plus 1 times a index n plus 2 plus an is equal to 0 for all values of n going from 0 to infinity. So we can write an plus 2 is equal to minus a fraction between an and n plus 1 times n plus 2. This is a recursive formula. That means that we can compute n plus 2 depending on an, and then n plus 4 depending on n plus 2, and so forth. We need two values to start to apply this recursive formula. We need a0 and a1. But a0 is the value of x at x0, and a1 is the first derivative of y at x0. So the initial conditions give us explicitly a0 and a1. So we can start computing it. So we write y of x as the infinite power series. Let's try to be more precise. We write it explicitly. So we have a0 plus a1x plus, now we have a2, that is something that depends on a0, so minus a0 divided n plus 1 times n plus 2. N plus 1 is 1, and n plus 2 is 2 in this case, because n is equal to 0, x squared, plus minus a1 divided 3 times 2. We have to look at what is 2 steps before that, x to the third. For x to the fourth, we again look 2 steps before. We take what is there and we divide by the power of x and the power of x minus 1. So a0 divided 4 times 3 times 2 times 1. If we keep going, we keep noticing that the odd powers only depend on the coefficients of the odd powers only depend on the previous coefficient of the odd power, and the coefficients of the even power only depend on the previous coefficient of the even power. So let's split those two. Only the even powers first, and only the odd powers second. The even powers, we see that they all depend on a naught. So let's take also a naught out of the equation. Then we have 1 minus 1 divided 2 factorial x squared plus 1 divided 4 factorial x fourth, and so forth. So each time we switch the sign and we divide by the factorial of that power. For the odd sector, we have, again, we can take a1 out of the equation, and we have x minus 1 over 3 factorial x3 plus 1 over 5 factorial x5, and so forth. If you recognize these two power series, they are the power series of the sine and the cosine. The cosine being 1 at 0 and the sine being 0 at 0. So we retrieve that yx is the sum between cosine x times a constant a0 and sine x times a constant a1. That is what we started out with.